this Zoom. And, oh, wait. I am ending the lecture portion of this Zoom, starting the office hour portion of this Zoom. What questions can I answer? Thank you, everybody who joined. If you have no questions, then we are done with lecture. If you have questions, I'm going to stick around for 15 minutes and answer any questions y'all have. Thank you, everybody. Thank you, thank you, thank you. Rosa. Oh, is that just a thumbs up?
Hey, Joe.
Yes.
I was wondering for that last problem that you did.
Yes.
Like, why is the V not squared? Like the V finals and all that?
Oh, keep in mind, we're looking at conservation of momentum. Kinetic energy is not conserved. So okay. You're saying, why is it not speed squared?
Yeah.
Yeah, keep in mind, kinetic energy is 1/2 mv squared, but momentum is mass times velocity. So 2 important things. One, kinetic energy is a scalar. There's no direction associated with it, and it depends upon the speed squared. Momentum is a vector. It's the mass of an object times the velocity, which means that momentum can be positive or negative depending upon whether the velocity is positive or negative. But momentum is never speed squared. It's always mass times velocity. Does that kind of help?
Yeah, totally.
Excellent. Other questions I can answer from anybody?
Joe, I had a question.
Okay.
Of example problems of chapter 9.
Example problems from chapter 9.
Yeah.
Let me see if I can, it's the easiest way to pull this up. Open. Physics 4A, chapter 9, example problems. Share screen. Okay.
So I'm looking at 9.7 and 9.21.
Hold on one second. Conceptual question or problem?
Problem.
Problem 9.7. Okay.
Oh, actually, I'm sorry. The practice problem that I'm looking at, it's actually the textbook online 9.7. My bad. It was from lecture, but the other one is 9.21. If we want to look at that first.
Okay, this one 9.21.
Yeah. The other problem is from the textbook, and it has a graph that's in proportion of tension versus change in position.
Hold on one second. Did I perceive what's happening?
Huh?
I'm just trying to see if I could pull this up easily.
Yeah, I'll wait a second.
Hold on one second. So this is chapter 9 homework problem. It's from the textbook?
Yeah, it's from the textbook online.
Homework, let me see, exams for a homework assignments, individual chapters, chapter 9. Let's go down.
Yeah, I believe you did it in class.
Okay, let me share this. It's cold out there. Okay, what question, what problem?
It should be 7, I believe.
This one?
Yes. Oops. I believe, oh no, it's supposed to be a 15 kilogram car towed from rest. So I don't know, maybe it was from the homework of mastering physics. I'm not sure.
Huh. Okay, why don't you just describe it to me?
Okay, yeah. So it's a 15 kilogram car being towed from rest, and the question is, what is the speed after being pulled 200 meters? And then there's a little chart that has a decreasing slope from 500 newtons, and it goes down to 0 newtons, crossing from 0 meters to 20 meters. And then when I look at the chapter 9 example problem 9.21, it's asking for the velocity of whatever it is that we're solving for, and it has a force versus meter
Got it.
position
So
graph.
I don't have that in front of me, but let's just pull up a whiteboard. So this problem, it basically is giving you some sort of plot of force in newtons versus position in meters,
Yes.
and it gives you the mass, right?
Yes.
What is the mass?
It's 0.5 kilograms.
And it gives you, I'm assuming, what the initial speed is.
Yes. It's 2 meters per second squared. Or 2 meters per second. Sorry.
And they want to know what is the final speed.
Yeah, so it's supposed to be set up that V final is equivalent to the square root.
So so the whole thing here is this is the work done by, so one, the work is going to be equal to the area under the curve.
Yeah. Yeah,
And
so
I
don't
have that problem, but you know, this is just, you have some kind of force versus position. You can get the area under the curve, which is the work. And I know that's going to equal my change in kinetic energy. So 1/2 mv final squared minus 1/2 mv initial squared.
Yeah.
So you're given the mass, you're given the initial speed, you can get the work from the area under the curve. So you're basically just solving this equation for what is the final speed.
Yeah, that's how it was put out in when you did it in lecture. And I understand that. But when I compare it to the other problem that we couldn't find, it was it went about it in a different way where you'd find the area, but then you'd make it equal to just 1/2. Oh, I guess it's because it's starting from rest that it would be different.
Right. So like if there was a similar problem where an object started from rest, and this whole term here would be 0. But the general equation is always this work equals my final kinetic energy minus my initial kinetic energy. It's just oftentimes something is starting from rest, so the initial kinetic energy is 0.
Yeah.
But in this particular case, it wasn't, because the object started off at 2 meters per second, not from rest.
Okay. 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 I think I get it now. I think like talking about it also helped me figure out why I was confused a bit. So
good. So keep in mind, yeah, if you have a plot of force versus position, you can get the work. If you have a plot of force versus time, you can get the impulse. Work results in a change of kinetic energy. Impulse results in a change of momentum.
Okay. Thank you, Joe.
You're welcome, Kendra. Any other questions? Anybody? Can we look at homework 11, number 10? I gotta start putting my homework in an easy, accessible homework. Oh, sneeze. All right, homework.
Bless you.
Thank you. Homework 1110. Mary, is this problem 10? Hold on for 1 second.
It's the homework on the it's number 10 on our homework, but it might be a different
Do you know? I
number.
don't.
While you're sharing your screen, I don't know how to escape. Let's see. Oh, I got it. And then it's 11.57, it says.
Question 57, 11.57. Block of mass M collides with block expression for the minimum value that will allow the second block to circle the loop without falling off. The collision is perfectly inelastic, perfectly elastic. So one, don't worry about the second part, perfectly elastic.
Okay.
So I'm not going to cover, there's a set of equations for what happens if I have a perfectly elastic collision where one of the objects is at rest. Just in terms of not having enough time, I'm not looking at that. But, and also just so you know, this problem is beyond what would be something that I would ask on the celebration just in terms of timing. But let me just kind of look at this real quick. So collides with a stationary block, find an expression for the minimum value that will allow the second block to circle the loop-to-loop without falling off. Oh yeah, so this is a great problem. Yeah, this would have been a great problem for final celebration had we been doing this live. So the situation is you've got a loop-to-loop, right? And you want to know, so one object's colliding with the second object, and you want to know how fast this thing needs to be moving so that this thing just does a complete loop-to-loop. Is that right?
Yeah.
So this is really a combination of conservation of energy and conservation of momentum. So one key thing is at the highest point, if you remember, there's this critical speed, which is the minimum speed something must be going in order for it to not lose contact with the surface here. So one key thing is it has to be going at this minimum speed, which is given by the square root of r times g. So r, keep in mind, is just the radius of this circular path, which means that I basically have, it's going to have a speed of whatever this is when it's at an elevation of 2r. Does that part make sense?
Sure.
It's going to be at a height of twice the radius of whatever this circular path is. So what you would use is, I would basically say that after these things collide, they're going to be moving with some speed. What I would say is the initial kinetic energy that they had right after the collision equals my final kinetic energy at the highest point plus my final gravitational potential energy at that point. So basically what I would say is 1/2 m1 plus m2 times v squared, this is v initial, equals 1/2 m1 plus m2 times this final speed squared plus mgy. This final speed is going to be the critical speed of the square root of rg. This final height would be twice the radius. So in essence, what you would do to solve this problem, and again, this is beyond what you would have to do for the celebration, but you would use conservation of energy after the collision to figure out how fast these things must be moving so that when it gets to the top, which is at a height of 2r, it has this minimum speed. Then once I figured out the speed it has to have after the collision, then I could use conservation of momentum to figure out how fast the lighter mass must have been moving beforehand. So this V initial, you're gonna basically use conservation of energy to figure out this, but this would really be the same as V final after the collision. So what I would do would be, I forget what these masses were, but if I call this M1 and M2. So what I would use is I would use momentum conservation to figure out that the final momentum after the collision equals the initial momentum before the collision. After the collision, in this case, if it's perfectly elastic or perfectly inelastic, they stick together and move as one. So I would have M1 plus M2 times V final, and this equals M1 times V1 initial, because M2 was initially at rest. So in this problem, you would first use conservation of energy to figure out how fast both masses must be moving after the collision so that they get to the top with this critical speed. So you're solving for basically V initial, which is how fast they're moving right after they collide and start moving together. But this V initial that you get for conservation of energy is really the final velocity that they had after the collision. I don't know if that was confusing.
No, that's really helpful. Thank you.
Yeah, awesome.
Yeah.
All right, so I'm going to stop this share for a second. Oh, there's another quick question on this.
Yeah, I was just going to ask, just clarifying that the external forces are, if the external forces are 0 is the only time that we say P final equals P initial.
If the sum of the external forces on a system is 0, then momentum for that system is going to be conserved. But that's the total momentum of the system as a whole, not any individual object.
Okay.
So, you know, if I've got 3 different objects and the sum of the external forces in all 3 objects is 0, then each object could individually change its momentum, but the total momentum of all 3 objects added together would be a constant.
Okay.
Can we look at the second conceptual question from quiz 10? How do I do that? Let's see. I'm trying to get better at being moving. Let's see if online resources, no. Document sharing, course home, all assignments, quiz 10, conceptual question. And let me do a new share. Did that come up? Can you see this chapter 10 quiz question? Somebody, can you guys see this one? Can't tell.
Yeah.
Yes.
Okay. Is this the one you had a question on?
Yeah.
Okay. A box of mass M is pressed against but not attached to an ideal spring of force constant K, a negligible mass, compressing at a distance X. After the box is released, the box slides up a frictionless incline as shown and eventually stops. If we repeat this experiment but use a spring constant having force 2K, and we want to know what of these is correct. Okay, is there a particular question you had, or you just want me to sort of touch on the answer to this?
I guess just touch on the answer. I thought that it was only one of them, but it's all 3 of them. And when I was trying to figure out the other ones, it didn't seem like it would make sense that it would go up twice as much or.
Can I write on this? Let me see if I can. Can I annotate this? Okay.
Or that the kinetic energy would be twice as much.
So the box will go twice as high as before. Twice as great. Okay, so the key here is basically that you're compressing the same amount, but the spring constant twice as much. And I want to know, how high does it rise? How much kinetic energy it has when the spring is launching it, and then the speed. So let me just do this on a different, it's closed, share screen, clear all drawings. Okay, so the situation was you've got a spring which we compressed a certain distance, delta X. After the spring was ejected, now this thing is moving with some speed, and then it's going to get up to some highest point, Y final. So 1, I know that the energy stored in the spring is 1/2 K times delta X squared. So in this case, the only thing that's changing is K. I'm now doubling it. So I have twice the spring constant that I used to have. So if that's the case, my new elastic potential energy is going to be twice as much. Right? If I had compressed the spring twice as much, then the new elastic potential energy would have been 4 times as much. But I'm compressing the spring the exact same amount, but now the spring constant is twice as much. So that means my new elastic potential energy is going to be twice as much. Well, if I think about it, what happens is first, all of this elastic potential energy goes into kinetic energy of the moving mass. And then all of this kinetic energy gets converted into gravitational potential energy. So if the elastic potential energy stored in the spring is twice as much, that means after the spring has completely extended, the mass will now have twice as much kinetic energy. And then when it gets to the highest point, it'll have twice as much gravitational potential energy, which means it'll go twice as high. So it's going to have twice as much kinetic energy, it's going to go twice as high. But in terms of the speed, remember, kinetic energy is 1/2 mv squared. So if my kinetic energy increases by a factor of 2, then my speed actually increases by a factor of the square root of 2. So K being twice as much means when I compress the spring the exact same amount, my elastic potential energy stored is going to be twice as much, which means that when the spring is no longer compressed or stretched, then it's going to give the mass twice as much kinetic energy as it had before, which means the final potential energy at the highest point will be twice what it was before. But 2 times the kinetic energy actually means the square root of 2 times as much speed. Whew. Okay. I am going to have to stop office hours for now. I'll be back tomorrow, and yeah, look forward to seeing you guys tomorrow. I will do a review. I will do some of the kinds of questions that you can expect to see for the celebration on Wednesday.
Thank you.
Oh, thank you so
I have
much.
a quick question. In your email you sent us, I don't know if you
Yes.
answered this, I'm sorry, I just jumped in here.
No
It
worries.
said PLC 10 is due. It's the create a one-sheet celebration.
Yeah. So it should be PLC 11. I sent another email right after that just saying it was a typo.
Oh, my mistake. Okay, I just
So the
clarified. Thank
just to
you
be
so much.
clear, the PLC that you're uploading by tomorrow, it's just having you start to organize. It's a 1-page cheat sheet. Even though the celebration's open notes, open everything, from my experience, if you don't actually create a cheat sheet and you're trying to flip through 2 or 3 books, people spend forever doing that. So it's much better to, even though it's open notes, open everything, have a 1-page cheat sheet.
Totally makes sense. Thank you so much.
All right, take care, Sheriff.